In this video, we'll look at the geometric series. Here we have a definition, the sum from n equals 1 to infinity of a times r to the n minus 1. Let's verify that this is indeed what we get. If we plug in 1 for n, we have a times r to the 0, which is just a. Then if n is 2, again plug in 2, and we'll have a times r to the 1, which is ar, and so on. An alternate way to write this is we could start the sum at 0. So n equals 0 to infinity, and then we'll have a times r to the n. You can verify on your own that this is indeed the same as this. It's just an alternate way to write it. Typically, I like to use this definition, but sometimes the second one can be helpful as well. Note that this series is going to converge when r is less than 1, the absolute value of r. So essentially, if r is between -1 and 1, we will have a convergent series. If the absolute value of r is bigger than 1 or equal to 1, it's going to diverge. Let's make sure we understand that. If r is equal to 1, we'll have a plus a plus a plus a plus a, and it's going to continue to get bigger and bigger and bigger. Or if r were 2, we would have a times 2 plus a times 2 squared plus a times 2 cubed, and you're going to continue to get bigger and bigger numbers. It's going to diverge. So the only time we can have a series like this that is going to converge is when these terms are getting smaller. And the way that happens is if these bases that we're raising to a power are fractions between -1 and 1. So if r is a fraction and we're squaring, cubing, raising the fraction to the 4th power, those are getting smaller and smaller and smaller, which means we're going to converge to a value. And the nice thing about geometric series, if they do converge, they're always going to converge to a divided by 1 minus r. So we have this nifty little formula that's going to give us the value that the geometric series converges to. It will always be a divided by 1 minus r. Let's look at an example. We want to determine whether the geometric series is convergent or divergent, and then if it is convergent, we can then find its sum. The first thing we want to do is notice that we're just giving a list of numbers, a list of fractions here. Let's see if we can write this as a sum using that summation notation so that we can, first of all, prove that it is indeed a geometric series, and from there we can use the nifty little formula to find the value that it converges to if it is indeed convergent. Notice that the numerator has all 5s in it. That's convenient. Let's factor out that 5. And notice that the denominator, all of these are divisible by 3, so maybe we can also factor out a 3 as well. What's going to be helpful is if we force the first term in the parentheses to be 1. That's going to help us with creating the summation notation that we need. So we're going to have 1 divided by 1 minus 1 divided by, we factored out a 3, so that 9 is now a 3, plus 1 divided by 9 minus 1 divided by 27, plus that continues forever. Now let's see if we can notice any other patterns. Notice the denominator. 27 is 3 cubed. 9 is 3 squared. This is 3 to the first, and we can think of 1 as 3 to the 0, if that's helpful. So let's do that. We have 5/3 times 1 divided by 3 to the 0 minus 1 divided by 3 to the first plus 1 divided by 3 squared minus 1 divided by 3 cubed. And again, that pattern is going to continue. Now let's look for a pattern. Notice we have 3's in the bottom raised to a power, and the top is all 1's. We know we have the constant out front, so we know 5/3 is there out front. That's going to be our a value. And what about the base? What is r going to be? It looks like we have 1 divided by 3, but we're raising that fraction to a power. So we have 1/3, and we're raising it to a power. In this case, that power is what we want it to be, n minus 1. Let's see if that is indeed the case. If n is 1, we have 1 minus 1, which is 0. That's here. If n is 2, we have 2 minus 1 is 1. That's here. That works. If n is 3, we have 3 minus 1 is squared. So 1/3 squared here. So that fits. But now notice that the signs are changing. We have a positive, a negative, a positive, a negative, and so on. Those signs are alternating. So right now, everything is positive. How can we make it alternate? We simply make that base a negative 1/3. And now, again, let's check to make sure that is true. If n is 1, we get a 0 power, positive base. That works. If n is 2, we get negative 1/3 to the first, which is what we have here. If n is 3, we get n 3 minus 1, which is squared, positive here, and so that works. So it looks like we have a formula for this series. Let's write it as a geometric series. We have n equals 1 to infinity. A is 5/3. R is negative 1/3. And we're raising that to the n minus 1. This now fits the definition for a geometric series. We have A is 5/3, and we have R is negative 1/3. Note that R is a fraction between negative 1 and 1, so we know it's convergent. Again, geometric series will converge when we have R, the absolute value of R, less than 1, meaning it's between negative 1 and positive 1. And we have that nifty little formula that will tell us what it converges to. That is A divided by 1 minus R. So let's just plug in what we know. A is 5/3 divided by 1 minus negative 1/3. Be very careful with the double negative. It's easy to make a goof there if you're not careful. 5/3 divided by 4/3, and that's going to give us 5/4. So this geometric series converges to 5/4. In our next example, we are again told it's a geometric series, and we want to know whether or not it's convergent or divergent. Let's first do what we did last time and see if we can write this in a way that will help us find the sum notation to prove that it is geometric, so we can then easily identify A and R, and from there determine whether it converges or diverges. Up first, I'm going to factor out the 3. I kind of want that first term to be a 1, so I'm going to factor out a 3 and go from there. So we have 1 minus, if we factor out a 3, that 4 is going to become 4/3. Then plus 16 divided by 3. If I factored out a 3, we need to multiply the bottom by 3. Then minus 64 divided by 9. Again, I factored out a 3, so we need to put a 3 in the denominator. And that's going to continue forever. Next, in the numerator, notice that it looks like we're getting powers of 4. We have 4 to the first, 4 squared, 4 cubed, and over here in the first one it would be 4 to the 0. And in the denominator, it looks like we've got powers of 3. We've got 3, 3 squared, 3 to the third, and again this one would be 3 to the 0. So let's rewrite it with that notation. Think of this first one as 4 to the 0 divided by 3 to the 0. Then minus 4 to the first divided by 3 to the first, plus 4 squared divided by 3 squared, minus 4 cubed divided by 3 cubed. And again, that's going to continue forever. So what do we have? We have 3 times, it looks like we have 4/3 as the r, and we're going to raise that to the n minus 1. Once again, let's pause and make sure that is true. If n is 1, we'll get a 0 exponent, which tracks up here. If n is 2, we have 2 minus 1, which is 4/3. Powers are 1, and so on. The only other thing we need to check out is notice it is alternating signs like it is in the previous example. So to fix that, we will put a negative for the r. And again, let's double check to make sure that's good. If n is 1, we have the 0, which is positive. If n is 2, we have 2 minus 1, which is 1. That makes it a negative fraction, which works. If n is 3, we get squared, which makes this positive. That works. So it looks like we have what we need. So we now have the sum from n equals 1 to infinity of 3 times negative 4/3 to the n minus 1. This fits with our definition of a geometric series. Here, a is 3 and r is negative 4/3. But remember, in order for a geometric series to converge, r has to be between negative 1 and 1. It has to be a fraction between negative 1 and 1. Negative 4/3 is outside this interval. That means this series diverges.